Hello, in the next few videos I'll be talking about strategies for estimating a population proportion. So let's say that we have a population, and maybe this is the population of US voters, and so I'm just going to guess, maybe that's around 200 million people. And you're interested in the population proportion. So the symbol that we use for that is just a lowercase p. And so we don't know what this is. Maybe in particular interested in p will be the proportion of the population who will vote for candidate A in an election. So this is an unknown, but we'd like to estimate this value. And so we're going to be looking at strategies for estimating the population proportion. All right. So let's begin by thinking about what would happen if we were to just take samples from this population. So maybe we would take a sample of 1,000 people. And from this sample we could calculate a sample proportion. So for that I would use the symbol p hat. But maybe I would take a different sample of the same size, n equals 1,000, and likely I would get a slightly different result from that proportion. So I'm going to put a subscript here of 1 for this guy and a 2 over here. And of course, we could do this over and over and over again. Sometimes we might have some overlap, but each time I take a different sample, I would have a proportion for that sample. So let's think maybe in sample 1, perhaps maybe 515 out of the 1,000 are going to vote for candidate A. So the proportion there would be 51.5%, or if you prefer decimal, 0.515. So maybe that's from the first sample. And from the second sample, maybe 480 intend to vote for candidate A. That's still out of 1,000, so that would be 48.0%, and so forth and so forth. Now, in another video, we've talked about the distribution of these. As long as certain conditions are met, for instance, we want to make sure that n times p times 1 minus p is at least 10, and we want to make sure that our sample size n is less than 5% of the population, so 0.05 times n. Okay, so but assuming those conditions are met, we know that the sample proportion has a bell-shaped distribution, so it's normal, and the center of this distribution is at the population proportion, p, and the standard deviation is p 1 minus p over n, and that's a big square root there. So this value, that's the mean of the sample proportion, whereas this quantity is the standard deviation of the sample proportion. The problem is, when we, well, actually before I get to that, so let's look at, get a picture of this. So it's bell-shaped, and let's see, here's the center, it's at P, and we could go 1, 2, and 3 standard deviations to the right, and 1, 2, and 3 standard deviations to the left. So let's say that in this particular population, even though as far as for estimating, we would not know this, but let's just say that the actual proportion in this population, P, is maybe 52. And so what would this is going to be also the mean for p hat, and how could we figure out the standard deviation for p hat? So I would need to take p, 1 minus p, divided by n, then the square root. So if I'm taking samples of size 1,000 from this population, this would be 0.52 times 0.48. That's p times 1 minus p all over 1,000, and then take a square root. So let's look at that. 0.52 times 0.48 divided by 1,000, and take the square root of that result, and this is approximately 0.016. So that's, I'm going to just round at 3 decimal places. So here is 0.52, and so 0.52 plus 0.016, that's 0.536, plus 0.016 again. This is 0.552 plus 0.016 a third time, and this would be 0.568. So those are 1, 2, and 3 standard deviations on the right, and one to the left-hand side. We've got 0.52 minus 0.016. That's 0.504 minus 0.016 again, 0.488, and minus 0.016 a third time, and this is 0.472. So, you may recall from the empirical rule that, for instance, 95% of my sample proportions, that's as long as I'm taking proportions from samples of size 1,000, 95% of those should be between 0.488 and 0.552. That's assuming that this is the true population proportion. All right. So let's go back then to the scenario here where I said I was pulling multiple samples. And let's see. This, I want to emphasize something. This distance is 2 of those standard deviations in the sample proportions. And so 2 times 0.016, which was 0.032. That was 2 times the standard deviation of the sample proportion. All right, so that's this. I want to just make sure it's clear where I'm getting this 0.032. That's this distance. So what I'm asking is, I know if I plus or minus 0.032 from this amount, that gives me a lower bound and an upper bound that would capture 95% of my sample proportions. Okay, so now let's go back and consider some of these sample proportions. So in my first sample, and this is all hypothetical, of course, I had 515 respondents who were going to vote for candidate A. That was 51.5%. What if I took this result and I did a plus or minus 0.032? So that would be 2 standard errors. Or if I took this result and did plus or minus 0.032. Let me show you what that would look like. So 51.5, that's somewhere over here. So this would be 0.515. So when I say that I'm going to add or subtract 0.032, basically I'm taking the distance of 2 standard deviations, and from this line I'm extending that amount. So that would go to here and to here. So that's, well, maybe a little bit longer. That's 2 standard deviations. So notice that if I look at this interval from here to here, what I want to point out for now is that that interval includes this center line. So remember, this center line is the true population proportion of 0.52. And that's captured in this interval where I took this first estimate and gave myself a little bit of wiggle room of 2 standard errors, 0.032. Now, what about if I took this second sample where it was 0.480? So 0.480, that one is somewhere down here. That's 0.480. Now, if I take the length of 2 standard deviations, and I would extend to here and to here, and now I have the can use my calculator and say 0.48 minus 0.032. That would give me a lower bound of 0.448, And then if I take an upper bound, like 0.48 plus 0.032, that would be 0.512. And now notice 0.512 is going to be just shy of this center line. Now, this interval from 0.448 to 0.512 does not include this center bar. So my first question is, if I were to do this maybe 100 times, so here's once and then twice, if I was continuing to do that, so I didn't just have one p hat or two, but I had maybe 100 of these guys. My question is, by the time I take each one of these and add and subtract two of my standard errors, so like I've done here and here, and to create an interval with a lower bound and an upper bound, how many of those intervals do I think would capture this mean, would be able to grab that when I look at extend it to by a certain amount below and above? Well, the trick to answer this is to think, well, if I were to get a sample proportion that was right here on this line and give myself 2 standard deviations. Well, notice that that line is 2 standard deviations from here. So that line, or that interval rather, would just capture this. And on the other hand, if I went on the other side and had a proportion of sample proportion of 0.552 and used that to construct an interval, then 2 standard deviations below it would just capture this guy, and 2 standard deviation above it would be going over here. But notice that any sample proportion that I have that's between here and here, by the time I add some bars that represent 2 standard deviations to the left and right, any of those would capture this center value of 0.52. Well, I need to ask myself, what proportion of the sample proportions are between here and here? Well, that's what we get from the empirical rule, 95%. So 95% of the time, or 95% of all of the intervals that I would construct, based on sample proportions, if I'm using this plus or minus 2 standard errors, 95% of all of those, would capture this, the true mean here of 0.52. So that's kind of the foundation of our strategy for constructing confidence intervals. We are going to start with one of these guys, and we call that a point estimate. So basically that is a particular value of a sample statistic. In this case, it'll be a value of of p hat. So we'll take one sample, we'll get a point estimate and to give us p hat. And then we are going to give ourselves some wiggle room, which we call margin of error. Now in this case, my margin of error was 2 standard errors, and so that can change, and we'll look at that in some future videos. But the symbol we use for margin of error is E. And the way that we formulate E is it has 2 pieces. One of them we call critical value, and the other is a standard error. Now in this case, the standard error, the way that I got this 0.032 was by taking the square root of p 1 minus p over n. And the critical value, we're actually going to use a z-score. I'll talk more about that in the next video. I hope you'll join me. All right, see you then.